primary surface area. And I also told you in the last class that there is a more complicated expression for fin surface area, which I intentionally did not do in the last class. So this is something that we have to do today. This is the expression which I have taken from the book by Lee. Now please pay attention and then let's try to understand each term properly. Okay, because if you just look at this expression, if you just read the book, it may not be very clear. And for this discussion, I have taken the help of some other figures from another book. So this figure to the top left, that is from Lee's book. But these two other figures are from a book by Shah and Sekulik. Okay, so I'll give you the reference of that book separately. So the fin surface area is given by this expression. Let's go term wise. So this is the first one. So this surface area corresponds to this surface area. I hope you're being able to see this. Okay, is it okay or is it too small? It's okay. Yes, I'm talking about this area which has been hatched in the figure. And facing this area is another area which is on the right hand side of this particular fin. Two such areas, as you can see from here. One area here and the other area which is on the left hand side of this fin. Okay. Now, how much is that area? To understand that, let's recognize that this is the flow direction. And look at this layer which is marked B1. B1 is the height of that passage through which fluid 1 flows, which we said is a gas. The other one is fluid 2, which is air, right? Now, if you follow the flow, it will move through this passage, and the length that this fluid gets in this direction is L2. Correct? Okay. Now let's talk about these two areas that I just now mentioned. The height of that area, okay, so it's a passage like this. Actually, this passage is kind of like this passage, right? Just compare, okay? You have to be a good observer of these figures. What I'm saying is, this flow passage, it's like a U. U, that is like this flow passage, okay? But you can also, this flow passage can also be, same area of the flow can be also calculated if you take this inverted U, which has been marked in the figure. I'm just using a figure from the book, and in the book, Lee has marked this one, so we'll look at this one, okay, which is equivalent to this, which is what I was referring to here. Okay. Now the height of this is B1 minus delta. Correct? This passage, height is B1 minus delta. What is delta? Delta is this width thickness. Okay. So this is B1 minus delta. Now, what is the length in the depth direction? So the length in the depth direction is actually from here to here, correct? But we don't need to take one fin, we can take all the fins together and calculate a total length of L2, right? So the area of one face is B1 minus delta times L2. Okay, so what I'm doing is I'm just shifting the second layer of fin, which is here. I'm shifting that to the left and aligning all the fins mentally, not in actual practice, right? So then the whole length that we get is how much? L2, correct? So the whole length is L2. So the area of one face like this is B1 minus delta times L2. But there are two such faces. So this is 2B1 minus delta multiplied by L2. Now we multiplied that by NF1. Now what is NF1? NF1 is the number of fins for fluid 1. Okay. In this layer. So here the number of fins is NF1. How do we get that? How do we get NF1? NF1 is actually this L1 divided by the pitch of the fins for fluid 1, right? So that is like saying you total get the length L1, divide that by fin pitch, then you will get the number, right? Okay. Yeah, so that's what we are doing, because if you don't write the NF1, then you have just taken care of the areas that you are getting for one fin, right? But there are NF1 fins. In this direction, you can count fins, right? 1, 2, 3, 4, 5, like that. So to take care of all those, you have to use NF1 here, correct? So this area which we have taken care of, it's this area which is called fin height area. Do you see my, it's difficult to see this cursor, this area. This is where my pointer is, right? In a classroom, the pointer seems small, but I don't think I know a way of increasing the size of the pointer. So hopefully you can read this fin height area and you can follow this arrow on the fin, right? Again, this figure is not in the book. This is from the book by Shah and Sekulik. Right, so this area is fin height area. This is 2 times B1 minus delta times L2 NF1. Right? Now AF1 has 4, AF1 is the total fin area. That has 4 terms. We just covered the first term. Now, as you can see, if you just read the book, it's not easy. Okay, so that's why it took me quite a bit of time to find other figures from other books and put everything together so that understanding this becomes a bit easier for you. Now let's look at this one, the second term. So the second term is in the F1 expression is 2 okay. And what is that area? Now that area is what is marked here. So this is fin edge height area. You can see where the fin edge height area is in the lower left hand side figure. You see what is marked? Hmm? It's this thing, right? This vertical strip, correct? Now, what is the area of that vertical strip? What's the height of the vertical strip? Hmm? B1 minus delta? Okay. So this is what we are trying to explain now. Hmm? So B1 minus delta is the height. What is the thickness? No. That's thin strip, fin edge height area. What's the thickness? Or you can, I mean, you shouldn't call it, I shouldn't call it thickness. It's length and breadth. Thickness is for more like three-dimensional things. Yeah. So that is delta by 2. It's not delta. Okay, important thing to remember. So this is delta by 2. Before we go any further, what is one fin? One fin is actually this thing. You know, this. That is one fin. This I explained in the previous class on Friday. Okay. So in this fin at the top you have delta, but here it's delta by 2. Correct? This area. So it's B1 minus delta times delta by 2. But there are 4 such areas. Why? Because you have one here, and two at the back of that fin. Correct? So that's why I multiply it by 4, so that that's why it comes out to be 2. This is the final expression. Okay. So this gives you this thing. What about n of 1? So this is the number of offset strip fins, which is basically this L2 divided by this length. Okay, this length we are calling delta 1. So n of 1 is L2 divided by lambda 1. You can see that? Okay. Yes. So we multiply it by n of 1, but multiply it also by nf1. Why? Hmm, hmm, hmm. Right. So what he's saying is basically, see, if you take one fin, right? If you just take one fin here, then in this row, how many such fins are there? NF1. Okay, for fluid 1. We are writing 1 because we are just considering fluid 1. Actually, if you change over to fluid 2, then all expressions will remain the same, just the subscripts will be changed from 1 to 2. That's all. So there's no point talking about 2 in F1. Right. So these are the number of fins in F1. But for each such fin, okay, there are similar offset fins at the back, one after the other in this following this, right? This one behind this one behind this, and many more. Actually, this will not be 3. This figure just shows 3, but there are actually large number of them. Correct? Maybe even thousands, who knows? Okay, so that's why we take n of 1 multiplied by nf1 to take care of all such fins, right? So that is offset, that is fin edge height area. So we're calling it fin edge height area. Then we also have to take care of fin edge width area. These are names from that other book by Shah and Sekulet. So your attention now should come here. Just follow the pointer. Okay, you see that red pointer? That's where it is. This one. Okay, so what's the area of this? We are calling it fin edge width area. Give 1 second. Yeah, so it will have like a PF1 by 2 minus delta by 2, right? What is that? If you look at this area, from this line to this line is how much? PF by 2. And just this small thing here is how much? Delta by 2. Okay. So PF1 by 2 minus delta by 2 is the length dimension. And the height is delta. Okay. So the height is basically from here to here. Okay. So that's delta. But how many such areas are there? Remember when we were doing this, we identified that there will be 4 such areas and we multiplied by 4. So here we have to do the same thing, right? So, so this requires some understanding of the geometry and thinking about what this is like. This is like this last fin here. Okay. I am talking about this particular fin. So what is shown in that figure, this one is kind of like the area which you get here. Is it okay or it's too difficult to see the pointer? I mean to say that I'm talking about this area. All right. So that small area is kind of like this area. So if you think about the geometry, think about this fin. Part of the top edge is covered by the previous fin, isn't it? That the third fin. So if we think about this one, the third fin is kind of like this, but the second fin actually blocks part of it, right? So that this much, actually this much remains free. Why are we interested in the free area? Because that is what the flow can see. Okay, so if you have doubt, please ask me now. Because otherwise, if you lose it now, then you will not, it becomes much harder for you to again go through the same argument at home. So yesterday I tried making a video on this one, but I had trouble writing these things on the slide because I was trying to use with the mouse and it's too difficult. I don't have a graphics pad sort of thing which could give me that sort of writing. But if you follow this class properly, this will be on video, so it will be now. This area is like this area. Anybody has a problem with that? Okay. So that area is PF by 2 minus PF1 by 2 minus delta by 2. Correct? And how many such areas are there? 2. Because you have this thing here, and on the back side also you have another area like this, but you don't have 4 because this side is blocked, right? Isn't it? Okay, so we got 2 here. Okay, then what we do is we multiply it by NF1 like what we did here, but we multiply this one by N of 1 minus 1. So why do we do minus 1? That is the question. I mean, it could have been like using the same logic here, it could have been just N of 1 multiplied by NF1. So why are we not doing that? We are not doing that because if you take the heat exchanger, then the first fin, so let's say this is the first row, okay? And let's say this is the last row, right? So this one and this one, this first row and the last row, they have the frontal part free. They can see the flow. They're not blocked by, I mean, the first row is not blocked by another fin here. The last row is not partially blocked by another row behind that, isn't it? So the front side of the first row and the back side of the last row, they together kind of give you one fin, which has to be excluded from this calculation. Okay, because those two faces are not partially blocked. Okay, so this just takes care of all the fins. This calculation takes care of all the fins. This term, all the fins that are partially blocked because of neighboring fins. Okay, but then we have to take care of the front face of the first row and the back face of the last row. Okay, so that will turn out to be 2pf1 delta nf1. So this is easy. pf1 into delta is what? pf1 into delta will be like this multiplied by this whole rectangular area. Fine. How many such areas are there? 2. Why? This first one, front face of the first row and the back face of the last row. Those are unobstructed. Okay, so that's the additional term which we are adding. This is additional term for fin edge area. So again, we are taking 3 kinds of areas. One is the fin height area, which is this one. And there is, of course, fin edge height area, which is a vertical area kind of thing, which is this one. And these two together, the third term and the fourth term together, take care of the fin edge width area, which is this one. Fine? Okay. I will not spend any more time on this one because I've already, I think, spent a lot of time and it's almost 10:30. But it's all going to be recorded. It's being recorded now. So you can watch this over and over again. If you have some doubts, you ask me. So that's the advantage of recording. If it was not recorded, then whatever I just say, that's it. It just doesn't stay with you. Okay, so this is the area calculation. The rest of it I have already described in the previous class. Rest of it is like, okay, you take the total area as the primary area plus fin area, as we have done in the other, for the other heat exchangers also. Whenever there are fins, primary area and fin area, just add the two. So this is the total area. And then there is some hydraulic diameter calculation. There is some uh, cross flow, free flow cross sectional area calculation. So these things you can just follow. Okay, this is all there in the book. And then remember that since these are fin surfaces, you have to get the individual fin efficiency. From that, you have to get the overall surface efficiency also. Correct? So these are required because ultimately you will get 1 over UA expression, which will have eta O1 for the overall efficiency of the first surface, eta O2 for the overall efficiency of the second surface. You can see some expression there. And okay, so once you get UA, you know how to use the effectiveness NTU method. But before you can calculate UA, of course, you need the heat transfer coefficient. No? UA calculation requires 1 over UA will also require 1 over H1A and 1 over H2A, like that, right? To get the heat transfer coefficients and the friction factor also you need, because sometimes the friction factor is required for heat transfer coefficient calculation, but also to get the pressure drop, right? So we have the J factor, we have then friction factor, then okay, so this is that problem which we read in the last class, example problem from the book. And this problem had these constraints. Again, we choose some N1, N2, N3. Then there's some primary area for fluid 1, primary area for fluid 2. These are calculated. Then AF1 is calculated. AF2 is calculated. This hydraulic diameter calculation. Ultimately, these are the Colburn factor, then friction factor, and heat transfer coefficient values. Remember, I said in the last class that they're almost the same because same geometry and same properties also. We took the property of the exhaust gas to be the same as the flue gas to be the same as air, right? So almost the same thing. There is a difference in the number of passages though, if you remember. Top one is a cold passage, bottom one is also a cold passage. Okay, so these are the individual fin efficiencies. So I'm sure you can do this on Thursday's class. And we use effectiveness NTU method. Then we got the effectiveness of the heat exchanger. We got all these temperatures, pressure drops. Okay, that's the entire problem. And with this, we stop discussing heat exchangers. Now, the heat exchangers that we have discussed so far are the shell and tube heat exchanger, pinned tube heat exchanger, and also plate fin heat exchanger. These three we have covered. There are also other kinds of heat exchangers, and there is a plate heat exchanger. I'll not cover that just in the interest of time. Okay, that's all. Because we have to go to something else. Now we have, from the beginning of the semester, what have we done? We first looked at the basic idea of this course and what is thermal design, what is the feasible design, why optimization is required. Okay, these sort of issues, just a broad overview. Then we came to heat sink, and we spent quite a few classes on heat sink. We understood fins also, hopefully a bit better. And now we are doing heat exchangers. Heat exchangers is done, so we'll go to heat pipe. Okay. So what are heat pipes? I briefly mentioned it, I think, once about heat pipes, but nothing much was covered previously. So let's look at this. So there are thermosiphons and there are also heat pipes. Thermosiphon, I don't know whether you had seen this before. Has anybody seen this? In textbook, maybe not in real life, but in some books. Has anybody seen thermosiphon? No. Um, but okay. What we do here for thermosiphon is that we have a tube from which air is evacuated and the tube is sealed and it has got some small amount of water here. Okay. And here you can, if you heat this, then some vapor can go up and then the liquid condensate can come down. Okay. Why will the liquid condensate come down? Obviously because of gravity, isn't it? So, and then it comes down, then it gets evaporated again, then it comes down. So you can have this sort of a system. But in case of a heat pipe, you do something similar. Here also, here you have again, you have a wick structure. Okay? And here the difference is, here you see that here it's getting heated at the top. Here heating was at the bottom. Now this is a heat pipe which is placed vertically. Heat pipes need not be placed vertically, but this one is in the figure. It's placed vertically. So you heat this and you generate a lot of vapor here. So this side there's a lot of vapor. Your heating is localized. Heating is only here, not throughout the length. So you're generating a lot of vapor. So the vapor will have, because of pressure difference, there's the less vapor at the bottom, more vapor at the top. So the vapor will tend to move down, right? And after that, it gets cooled here. So the vapor gets condensed into liquid and the liquid rises up the wick. Okay. Now this is something which gravity is not obviously not doing, right? In this case, the condensate came down because of gravity, but here in the heat pipe, the wick is doing something. Something is happening, so the liquid is actually going up, right? So effectively, what you are doing is you are transferring heat and taking it out from here. So this is transporting heat. This device, which you are calling heat pipe, it's transporting heat. So effectively, it has got very high thermal conductivity. This device, as such, has, we can think of it as having some thermal conductivity, which is very high. Okay. Is this useful? We understand from this figure that it's transporting heat. You know, heating at the top and taking out the heat from the bottom. Is it useful somewhere? We'll see that now. So again, this is another heat pipe, which is now in this one it's shown as a horizontally placed heat pipe, and you can supply heat here. So this is an evaporator section. This has got some liquid here, so the liquid gets evaporated. So the vapor moves in this direction because you're generating vapor here. So the vapor moves in this direction, and this is a condenser section where liquid is taken, vapor is cooled, and you get liquid, and the liquid moves through the wick and goes in this direction. So this is a wick. Okay. So what is a wick? W-I-C-K. Can you check what is a wick on your phone? Krishan? So you are spending a lot of time on mobile during the lecture, so maybe you can do the search. Okay, but obviously that's not what's happening here, right? Okay, that's what it says. Mhm. Which dictionary? Dictionary.com or what is the site? Just Google. Okay, so we have to see what is a week. I mean, I'm not satisfied by what you said. We have to understand physically what a wick is. So you have seen this wick in a candle, right? Okay, so what is it actually? Hmm. No, that's okay. But what is the structure of the wick? I mean, physically, what is it? I mean, what is it made up of? So it can be a mesh. Okay, so that's one question. What is a wick? What's the structure of this? The other thing that we can think about is that where is this used? So this is one answer. So in a laptop, this is used. So laptop where more heat is generated, where there's more CPU sort of thing. Okay, so from there you can place the that evaporator section of the heat pipe, so it will pick up heat from there. It will take some of that heat somewhere else, where there can be a fan, which there will be cooling, and then the heat can be transported. Okay, so this is an extremely important component of what you're using um, in a laptop. Okay, so this is again another figure, basically same thing, but it just tells you that this wick, it has got liquid in it, and the liquid in the wick looks like this. So this has a name. This thing which you see, okay, this has a name. What is it called? This curvature which you see. I mean, I'm talking about this thing. What is it called? Hmm? So if you have a test tube or a manometer or something, what is this called? Interface is okay, but there is also meniscus. So these, right. So this thing, this interface looks a little different from the condenser interface. The interface at the evaporator and the interface at the condenser, they do not look the same. Correct? Why? Because in the evaporator section, liquid is getting lost, right? Evaporating and all that. Whereas there on the condenser side, there is condensation. So it's got more liquid and it's like more level liquid surface and a less curvature. Okay. Now, we are talking about the wick. So this, if you take a heat pipe and if you cut it, this thing, if you cut it and look it from the side, this is a photograph. So these are photographs which are available in the public domain, and I just picked it up by doing a Google image search. So you can do something similar also. Okay, so this is the wick. This is a wall, right? This is the wall, correct? So the wall is kind of showing up like a whitish thing. So this is the copper wall. To me, it looks like a copper heat pipe, okay, from the color. That's outer thing. But the inner one, which is thick, looks granular, kind of like porous material, isn't it? So that is the wick. So this is one, and let me see. I think I have got other wick pictures also. Yes, so these are different models, different types of wicks. So you can I think one of you said it can be a mesh, right? So these are screens, which are multiple screens, which are attached to the underside of the wall, right? This is just a schematic which just tells you about different possible wick structures. It's not like in a particular heat pipe you use all three. That is not what is meant, right? So these are screens. Now this is sintered materials. This is wick. The wick can also be grooved material. Okay. Ultimately, this sort of structure will give you this uh, kind of meniscus. One kind of meniscus at the evaporator side, another kind of meniscus on the condenser side, and then these things are going to do something which will drive the liquid through the wick, even if gravity is opposing it, right? And this is because of some kind of a fluid mechanics action. So you call it, what do you call it? Capillary action. So this is capillary effect. So the wick prepares some kind of capillary structures. And because of which you get capillary effect and the liquid gets pumped. The liquid actually is getting pumped. These are pumps, right? And they just by doing this kind of structure, you have generated pumping effect, which will push the liquid uh, through the wick structure from the condenser to the evaporator. And then this becomes a loop, right? Liquid gets evaporated, moves through the center of the heat pipe to the condenser section. In the condenser, it loses heat, becomes liquid, and the vapor becomes liquid, and the liquid then goes through the through the wick to move towards the evaporator. Then the same thing continues. So you don't have to keep water or keep adding water or something, right? If you have a heat pipe, it has the liquid and keeps doing all this and keeps transporting heat. Okay. So this is I like heat pipe in the sense that at least this is something new to you. Heat exchangers, you already had some kind of understanding. Heat sink, maybe you knew less than heat exchangers, but of course you knew something about fins, you knew something about fin array, you knew something about overall surface efficiency. Okay, but this is kind of, most of it is new. Okay, and this has got extreme importance in cooling of electronics also, as you can see. Okay, it's also used in space applications, transferring heat from one part of the space module to another part of it. Okay, then these are other photographs. So you can see meshes. So this is also looks like this is also mesh, and uh, this looks a bit coarse. This looks fine mesh, and these appear to be sintered. Okay, this thing, if you again cut open, then it will look like this. Second figure is the first heat pipe on the left and the second heat pipe on the right. They're basically, I think, both are sintered. Is what I'm thinking. And we also spoke of grooved surfaces. You saw one which is like grooved. So this is the grooved one. So you can see like these kind of like teeth, right? Not teeth, serrations. And you can see these things here also. So again, giving you the small passages where these menisci can form. Okay, something similar to this only. Ultimately, this here also different menisci will form. Right, menisci is the plural of meniscus. So that happens here. This is it seems a bit more on the macro scale, so it's easier to understand. Here it's more difficult to see because there's a very small pores. Okay. But groups also you can make. I mean, groups here. This is not a photo, obviously. This is a 3D drawing that somebody has done, a 3D CAD model or something. So this is it looks like big uh, inner serrations, but of course it will not be so big. It will be much smaller, as you could see in this one. These are not so big, obviously. Okay. And this one, sorry, this one is called wrapped screen wick. Okay. Then there is also sintered porous metal. Then there are grooved wicks, things like that. So we'll understand this because today is the introductory lecture when it comes to heat pipe. Today I obviously didn't have much time, but this is kind of important to our understanding that if you have small surface pores, then the capillary pressure difference that you create that will be higher. Okay, we don't understand it now. We'll understand it because we'll do some analysis. We'll do some simple analysis. Actually, when it comes to heat sinks and heat exchangers, we took a more applied approach. Actually, this course is more applied. But here, since you may not know the fundamentals of heat pipe, we have to do some fundamentals also. Some lecture, maybe tomorrow's lecture, will spend some time on the fundamentals of this also. Then we understand this statement that, okay, why are pores important for generating pressures? And if we want smaller pores, is there an advantage? Do we get higher pressure generation? Pressure is required for what? To push that liquid through the wick, right? Okay, so we'll do all that in tomorrow's class. So yeah, before you go, let me also tell you this, that I'll prefer if you today sometime you